So friends, we look here into the example uh, for no obtaining the Bode plot for a given transfer function. Now we have seen individually here how to obtain no Bode plot, the magnitude curve and the phase angle curve when we have uh, considered factors individually, like a real zero, a real pole, or term k by s to the power r, or complex conjugate poles, right? So individually we have seen how we can obtain the Bode plot for them separately. Now when we have all the terms included, right, and as given here, we need to now find out for this g of s its frequency response. So we will go as per the Bode plot method techniques which we have discussed in obtaining the frequency response of obtaining magnitude variation against log omega and the phase angle variation against the log omega. So now we know that the first step which we need to do is to convert the given transfer function here. The given transfer function we need to convert into the uh, time constant form, right? So what we do, we first get the given g of s into a time constant representation form. So you can see for this 0 to be in time constant form, we take 2 common, right? So it will be 64 into 2, and here it will be s by 2 plus 1 for that 0, then by s. Then for this pole to be in time constant form, we take zero point 0.5 common. So zero point 0.5 is nothing but 5 by 10, that is 2 will come in numerator, right, when we take zero point 0.5 common here. So and in pole it will be now 2s plus 1, right? S by zero point 0.5 is 2s plus 1, and here I will take 64 common. So when I take 64 common, so there will be 64 here outside, right? And then I will be getting something as s square by 64 plus 3.2 by 64 s plus 1. So when we see all of this, 64 gets cancelled and 2 into 2 4. So in time constant form, this is how the transfer function looks like now after completion of step 1. So the open loop gain k in time constant form is now 4 here, right? K is equal to 4, you can see here. Next we do here is we obtain the sinusoidal transfer function by replacing s with j omega. In s of omega, we will get g of j omega. That is called a sinusoidal transfer function that we did here, right? Now we are set ready to uh, look into development of Bode plot. So what we do, first we begin with the term k upon j omega to the power r, this term, if present at all in the transfer function. And in our case, it is, and the term turns out to be 4 upon j omega, right? So this is the term which we have identified to obtain its individual asymptotic plot first. Now we know when we have such a term, the corner frequency is none. That means the magnitude plot holds for all values of frequency throughout the frequency without any without any what modification or change in at certain frequencies. So there is no corner frequency for such a term k upon j omega to the power r. Now, what will be the magnitude plot or asymptotic plot for this on the for the Bode plot? So we have seen that it will be a straight line of slope 20 log of k, straight line of slope 20. sorry, yeah. So here it will be what? 20 log of 4, right, upon omega. That is what it will be, the magnitude curve, the magnitude plot, 20 log of mod of gj omega. Here for this term only, it will be 20 log of, for considering individually this term, it will be 4 by omega, the magnitude. So it will be equal to, yes, what it will be equal to? It will be equal to minus 20 log of omega plus 20 log of 4. And 20 log of 4, if you evaluate, turns out to be 12 dB. So the H intercept is this much, right? And this passes through what? It passes through, the straight line passes through 20 log of 4 at omega equal to 1. So we know that the plot will look like this. If this is omega equal to 1, then straight line here will pass through something 20 log of 4, that is 12 dB, right? So if this is 12 dB, so if this is 12 dB at omega equal to 1, this is the point. Then from this point, there will be a straight line passing with a slope of minus 20 dB per decade. This is the individual plot for the term 4 by j omega. So I hope you understand, right? And in and this is the plot. Remember this straight line that passes through 12 dBs at omega equal to 1 with a slope of minus 20 dBs per decade. This is the asymptotic plot for the term 4 by j omega. And this straight line remains no for all frequency omega. Since there is no corner frequency at which it will change its course, the straight line continues for all values of frequency for this particular term, right? And that's why we say at low frequency, when we need to find out the resultant uh, magnitude plot, when all the factors are considered here, in the low frequency, the magnitude plot will be dominated by the term 4 by j omega to the power r, right? This term will be dominating in the low frequency region, because other terms at their respective corner frequencies, no, in low frequency region, they would be contributing 0 dBs line. So in low frequency, for a resultant magnitude curve, the overall Bode plot will be dominated by the term k upon j omega to the power r. I hope you understand and agree with me at this point, right? And when it comes to the phase angle contribution by the term, the phase angle contributed will be here given by what? Yes, we know the phase angle will be given by, since angle contribution by constant is 0, and by 1 by j omega term, the phase angle contribution, right? When we take the phase angle contribution, it will be equal to minus tan inverse of infinity, right? Since real part is 0, so it will be tan inverse of omega by 0, that is tan inverse of infinity, and tan inverse of infinity is what? 90 degrees. So it will, since this is in denominator, a pole at origin, the overall phase contribution by this term considered together will be a constant minus 90 degrees at all frequencies, right? At all frequencies, if you look at phase angle contribution, if this is minus 90-degree line, then it will contribute a constant line for all frequencies. That is about the phase angle contribution of this term. Then we come to here, yes, get the pencil back. Yeah. Then when we come to next factor, that is a pole 1 plus j2 omega, right? So if you look at this, the next term of interest will be for us what? 1 by j 2 omega. Now I am arranging here the term with lowest corner frequencies, right? Remember, as we see, the corner frequency was none for the first term. For this factor, 1 upon 1 plus j2 omega, its corner frequency is, yes, 1 by 2. The reciprocal of coefficient of omega gives the corner frequency. So 1 by 2, that is 0 0.5, is this corner frequency. Corner frequency of this pole is 2, reciprocal of coefficient of omega, it will be 2. So for 0, this 0, the corner frequency is 2. And for this, when u is equal to 1, that is when omega is equal to omega n, here omega n is 8. So we have corner frequency for this as 8. So I am arranging terms in their increasing order of corner frequency, starting with none, then the lowest corner frequency, then further no higher, next higher corner frequency. So this term has now lowest corner frequency. I am accounting it here, just a guidance, not mandatory. Now this factor, when we see, we have we already have seen, right? So its corner frequency is 0.5. So it will be interesting to quickly obtain the Bode plot here for this. It will be given by, yes, where is some space I need? Let me draw it here. So the corner frequency identified is 0.5. If this is 0.5 line, omega equal to 0.5 like vertical line, then below this corner frequency, the magnitude plot will be 0 dBs line, right? Remember, the y-axis is dBs line and x-axis is logarithmic line. So it will be 0 dBs, and above corner frequency, it will be a straight line of slope minus 20 dBs per decade, a pole. So it will be minus. So this is how will be the plot for the factor 1 upon 1 plus j2 omega. This will be minus 20 dBs per decade. Okay, that's what we have written here, right? For omega less than omega 1, that is corner frequency 0 dBs, and for higher values, it will be straight line of slope this much. And phase angle contribution of this, it will be how much? Phase angle will be given by minus tan inverse, minus because it's a pole, it is in denominator of transfer function, minus tan inverse of imaginary term, that is 2 omega divided by real term, that is 1. So minus tan inverse of omega. So at omega equal to 0, tan inverse of 0 will be 0. At omega equal to infinity, it will be 90 degrees. So as omega changes from 0 to infinity, the phase angle changes from 0 to minus 90 degree. Minus because it is a pole here, right? So that's what is the phase angle contribution of this particular term in the phase angle plot. So we know Bode plot has two plots, right? One is the uh, magnitude plot, another is what? The phase angle plot. So that's how we get two plots on the same page, right? Semi-log graph sheet. It is log omega here. Now we go to next factor of no higher corner frequency, that is a 0, and its corner frequency is going to be, yes, reciprocal of coefficient of omega, that is 1 by 0.5, and that is 2. So for this I can draw its magnitude plot here. Here is logarithmic axis omega. So corner frequency is 2. Let me identify this as corner frequency equal to 2. I will draw a vertical line here at omega equal to 2, right? This is omega equal to 2, the corner frequency. And below that corner frequency, for this factor alone, it will be 0 dBs line. And above it, it will be a straight line of slope plus 20 dBs. Since it's a 0, it contributes above its corner frequency, a straight line of slope plus 20 dBs per decade. And then similarly for this complex conjugate term, which is rearranged here, we have seen in our earlier discussion, its corner frequency is, yes, how much? Let us say its corner frequency is 8. So this is omega equal to 8, right? It is here, we can see. So it contributes 0 dB's line below its corner frequency and a straight line of slope minus 40 dB's per decade for higher frequencies from its corner frequency of 8 radians per second. So here this line is having a slope of minus 40 dBs per decade. So in this way, we have identified the individual magnitude plots of all the terms, and their respective phase angle contributions can be just found as told for other factors. You have to simply take for this case, right? It will be what? It will be minus, right? Then tan inverse of real part, that will be 1 minus u square by what? Yes, it's tan inverse of imaginary by real. So imaginary here is what? Yes, zero point 0.4 u. Sorry, it should be minus tan inverse of zero point 0.4 u by real part, that is 1 minus u square, right? So that's how you have to find out, right? By no higher by varying omega from 0 to what? Infinity. You have to correspondingly see the complete phase angle contribution. So here you can see when omega tends to 0, omega is 0, the phase angle phi will be given as 0, right? So 0 upon anything will be 0. So as omega tends to infinity, the phase angle phi will be now given by what? Minus tan inverse of what? Here again it is coming out to be what? 1 by infinity. So tan inverse of 0, right? 1 by infinity will be 1 by infinity will be 0. So tan inverse of 0 here in this case will go to what? Plus minus 180 degree, right? So that's how the angle will proceed from angle phi equal to 0 to what? Angle phi equal to contribution of plus minus 180 degree by this factor of complex conjugate poles. So I hope it's easy and clear. Quickly let us see the resultant the magnitude curve for the complete case. We have seen individually how the magnitude and phase angle plots are obtained. Now, once we know that these are the individual asymptotes and the phase angle contribution, for finding out the resultant magnitude and phase angle plot, it becomes very easy. So you can see here they have lined up corner frequencies in their increasing order, starting with lowest corner frequency of 0 0.5 that was corresponding to a pole. Then there is a 0 at corner frequency 2, and further at other higher corner frequency of 8 there are two complex conjugate poles. So this corresponds to what? I will write it down here. This corresponds to corner frequency of a pole, simple pole, real pole. This corresponds to a corner frequency of simple 0, and this corner frequency corresponds to presence of complex conjugate poles in the given transfer function. Complex conjugate poles, right? So we know in low frequency region, that is below zero point 0.5 radians per second, it is the term k upon j omega to the power r that will be dominating. And we know what is asymptotic plot contribution of this term, which we have seen. That was a straight line passing through 12 dBs at omega equal to 1. So here you can see the omegas are labeled here, different values of omega. So when this is 0.5, right? Okay, so it will be zero point 0.1. We are starting with 0.1, right? Then we will have got what? So 1 second, we have here, yeah, yeah, this is there. So this will be for me omega equal to zero point 0.1, right? One block later, this is will be omega equal to 1, right? One block later, this actually it should be further here zero point 0.1, right? So since it's zero point 0.5, okay, it will be further this side somewhere. It's not visible in this case, but this is omega equal to 2, so this is omega equal to 1, right? This is omega equal to 1, and this is omega equal to what? 10, another block, right? Beginning of another block. So in a low frequency region it is this term, and for us what was the factor? The factor was is 4 by j omega, right? So for us this factor was 4 by j omega. Yeah, for us this k was 4 and r is 1, so this was 4 by j omega, and for this it will be 20 log of 4, that is 12 dBs, passing through 12 dBs at omega equal to 1. So this is omega equal to 1. You see this is a straight line, right? This, right, with no light faded line, not a solid or bold line, a faded line, not a bold line. This line passes through 12 dBs at omega equal to 1. This is omega equal to 1 line, right? This is omega equal to 1 line. It passes through 12 dBs. You can see that this is dBs, right? This is your dBs axis and this is your log omega axis. So it passes through 12 dBs with a slope of minus 20 dBs per decade. That is what we also arrived at, no, said about. So in the low frequency region, that is for less than the smallest of all corner frequencies, in this case it is zero point 0.5, the magnitude plot will be dominated by a straight line of slope minus 20 dBs per decade passing through 12 dBs, right, at omega equal to 1. So that is what we see when we extend this line, right, beyond, or below omega equal to zero point 0.5, right, on the left hand side. So this is that straight line. Okay, so this straight line will be made bold till you hit first corner frequency, the smallest in this case is zero point 0.5 radians per second. Here there is a pole, and at pole what happens, the incoming magnitude plot uh, modifies with additional slope of minus 20 dBs per decade, because there is a pole. A pole contributes a asymptote of slope minus 20 dBs per decade, right, at its corner frequency. And so till here, the straight line was minus 20 dBs per decade. After zero point 0.5, it will be minus 40 dBs per decade. So you can see that this straight line now from zero point 0.5 onwards has bended further, right? Okay, so it has now become minus 40 dBs per decade because it meets a pole at this corner frequency of zero point 0.5, and that is listed here, right? You can see here this is minus 40 dBs per decade. Now this will be made bold and thick, and it will run till it meets another corner frequency, that is at omega equal to 2, and that is where a zero exists, a zero lies, and 0 adds a asymptote of slope plus 20 dBs per decade. So what happens here from onwards to this minus 40 dBs per decade plus 40 dBs per decade are added, and the resultant will be minus 20 dBs per decade, right? So from here onwards, corner frequency of 2 radians per second, your resultant magnitude plot now becomes what? A slope of minus 20 dBs per decade. That is what is, no, you can see is written here. This straight line is of slope minus 20 dBs per decade, whereas this incoming straight line at omega equal to 2 was of slope minus 40 dBs per decade. Now this continues till it meets next corner frequency, that is at omega equal to 8. That is here it hits the no Bode, the semi-log paper, it hits here. Then here there are two conjugate poles. So a asymptote of minus 40 dBs per decade is there. So to this minus 20, now a slope, a asymptote of slope minus 40 dBs per decade is added. So resultant asymptote curve from there onwards will be minus 60 dBs per decade. So you can see here from here onwards, the resulting slope of the asymptote is minus 60 dBs per decade. So that's how whenever the incoming asymptote line meets a corner frequency, its slope gets changed by either existence of pole or zero. A simple pole will add minus 20 dBs per decade, or a simple and individual zero will modify with plus 20 dBs per decade, or complex pole with minus 40 dBs per decade. So that's how we have made the resultant magnitude curve here, which you can see here. And similarly, we obtain the resultant phase angle characteristic by adding no respective phase angles where we have seen earlier, right? So if I can get it little erased. So this is the resultant phase angle characteristic. This one, right? Let me get the pencil here. This one is the resultant phase angle characteristic. We have already seen individual phase angles, right? How they are obtained for the individual terms. When we add all those phase angles, right, at the different frequencies for which we have obtained them, this is the resultant phase angle curve that we get, right? So that's what I wanted you guys to understand, and I hope it's clear. Let's stop here first now.